3 years ago, a customer rolled a 2003 Honda Accord into my shop with 387,000 miles on the odometer. Original engine, original transmission. The only major work it had ever needed was a timing belt at 188,000 miles and a water pump at 260,000. I walked around that car twice before I believed the mileage was real. That same week, I had a 2015 Ford Fusion on the lift with 89,000 miles and a blown engine. Brand new car by comparison, dead at 89,000 miles. That contrast haunted me, not because it was unusual, because it wasn't. I've been a mechanic for 19 years. I've worked on everything Chevrolets, BMWs, Volkswagens, Toyotas, Hondas, Fords, Mazdas, Mercedes. I've torn down engines from every major manufacturer. I've measured tolerances, analyzed failure patterns, documented what breaks and when, and the data I've collected over nearly 2 decades points to one undeniable conclusion. Japanese vehicles outlast their American and European counterparts by a margin that cannot be explained by materials alone, or technology, or even quality control. The real reason goes deeper than any of that. It starts with a philosophy. And once you understand the philosophy, you'll never look at a car the same way again. The foundation, 2 completely different goals. Western automakers and Japanese automakers are not trying to build the same thing. That sounds obvious, but the implications are enormous. American and European manufacturers build cars to a price point. Every component in every vehicle has a cost target assigned to it before a single engineer draws a single line. The question isn't, how good can we make this part? The question is, how good does this part need to be to last through the warranty period without triggering a recall? Those are fundamentally different questions, and they produce fundamentally different results. Japanese manufacturers Toyota, Honda, Mazda specifically operate under a principle called Kaizen. It's a Japanese word that translates literally to continuous improvement, but it means something much deeper in practice. Kaizen isn't a strategy. It's not a quarterly initiative. It's a cultural operating system that governs every decision from the boardroom down to the assembly floor. Under Kaizen, the question is never, how cheaply can we build this? The question is always, how can we build this better than we built it last year? Here's how that plays out in real money. When an American automaker identifies a way to save $6 per vehicle, by substituting a cheaper alloy in a suspension component, that change goes through. $6 multiplied across 1 million vehicles is $6 million. That's a line item that makes shareholders happy. When a Japanese automaker identifies the same $6 savings, they run the component through extended fatigue testing first. If the cheaper alloy shows any increase in failure rate beyond 150,000 miles, the change doesn't happen. The $6 million stays on the table. The better part goes in the car. I have watched this exact dynamic destroy American vehicles for 2 decades. Cost-cutting decisions made in boardrooms translate directly into failures I see on my lift. The customer pays for it. The manufacturer's thought price already moved on. Overbuilt by design here is the single biggest mechanical difference between Japanese engineering and Western engineering. And it's something most people never hear about: safety margins. Every mechanical component has a specification. A bearing might be rated to handle a certain load. A connecting rod bolt might be torqued to a specific value. A valve spring might be designed to cycle a certain number of times. What separates Japanese engineering from Western engineering is how far beyond that specification the component is actually built. Western manufacturers typically build components to handle 100 to 120% of the maximum expected load. That means the part will survive everything the engineers expected to encounter, with a small buffer for unexpected stress. It's efficient. It minimizes material cost. It keeps weight down. And it produces vehicles that perform well until they don't, and when they don't, it's usually catastrophic. Japanese manufacturers build components to handle 200 to 300% of the maximum expected load. A part that needs to survive 100,000 stress cycles gets designed to survive 250,000. A bearing that needs to handle 800 pounds of force gets built to handle 1,800. That's not a small buffer. That's a fundamentally different definition of what good enough means. I've seen this inside engines. When I crack open a high-mileage Toyota 2GR FE V6, the engine in Camrys, Highlanders, and Avalons, the internal components at 200,000 miles often look like they belong in a much younger engine. The cylinder walls have minimal scoring. The bearing surfaces are clean. The tolerances are still within spec. Compare that to a comparable American or German V6 at the same mileage, and you're often looking at worn journals, glazed cylinders, and sludge accumulation that tells the story of a component that was built to barely survive, not to thrive. Toyota's 2AR FE 4-cylinder, one of the most common engines on the road, has documented examples exceeding 400,000 miles with nothing more than routine oil changes and scheduled maintenance. The engineering that makes that possible isn't magic. It's deliberate, intentional over-engineering at every level. The tolerance question. There's a measurement I take on every engine I rebuild: clearance tolerances. The gap between moving components, piston to cylinder wall, crankshaft journal to bearing surface, camshaft lobe to follower tells you everything about how an engine was designed to age. Tight tolerances mean more precision during manufacturing, higher cost, better oil fill maintenance, and dramatically longer component life. Loose tolerances mean faster, cheaper manufacturing, but more wear at every contact point. Japanese manufacturers hold tighter tolerances than anyone else in the industry. When I measure the piston-to-wall clearance on a Toyota engine against the specification in the factory service manual, I'm often finding components that are within 1 or 2 ten-thousandths of an inch of the target. That level of precision requires better manufacturing equipment, more rigorous quality control, and more time on the production line. It costs more. Toyota pays it anyway. The consequence of tight tolerances is an oil film that actually does its job. Engine oil doesn't just lubricate, it creates a protective layer between metal surfaces that prevents direct contact. When tolerances are tight, that oil film remains intact even under high load and high temperature. When tolerances are loose, the oil film breaks down under stress, and metal contacts metal. Every time that happens, both surfaces wear. Multiply that across millions of cycles over hundreds of thousands of miles, and the difference in component life is enormous. Honda's engineering team has published internal data showing that their VTEC engines maintain oil film integrity at tolerances that would cause film breakdown in typical American or European engines. That's not marketing. That's the physics of why those engines last. How they test before it reaches you. Toyota runs engines on dynamometers for the equivalent of 500,000 simulated miles before a new engine design enters production. Not 100,000 miles. Not 200,000 miles. Not 200,000. 500,000 miles of simulated stress, thermal cycling, load variation, oil starvation testing, cold start cycles in sub-zero conditions, sustained high RPM operation. If anything fails during that 500,000-mile simulation, the engine doesn't go into production. The engineers go back to the drawing board, find the failure point, redesign the component, and run the test again. From the beginning, American manufacturers run comparable tests at 150,000 to 200,000 simulated miles for most engine families. That's not a small difference. That's a completely different standard for what constitutes a proven, production-ready design. Mazda's Skyactiv engine program went through 14 complete redesign iterations before the Skyactiv Active G engine entered production. 14 times, Mazda engineers tested a design, found something they could improve, and started over. The result is an engine with a high compression ratio that most manufacturers said was impossible to achieve without premium fuel. And it works reliably across hundreds of thousands of miles. The testing difference matters because failures that appear at 180,000 miles in real-world use show up predictably during extended dynamometer testing. If you don't test to 500,000 simulated miles, you never see the failure mode that appears at 180,000. You ship the engine, your customers drive it, and they find the failure instead. If this is genuinely changing how you think about what's under your hood, consider subscribing. There's a lot more where this came from. Assembly. The human element here is something that almost never gets discussed in automotive journalism. The difference in how Japanese vehicles are actually assembled, not just designed. Toyota's production system, The Toyota Production System, or TPS, is the most studied manufacturing methodology in the history of industrial production. Business schools teach it, manufacturers in every industry attempt to copy it, and the core principle that makes it different from every other assembly system ever developed is this: any worker on any Toyota production line has the authority and the responsibility to stop the entire line if they identify a defect. Not to flag it for a supervisor, not to fill out a report, to stop the line. In most manufacturing environments, stopping the production line is a catastrophe. Every minute the line is stopped costs thousands of dollars. Workers are incentivized, explicitly and implicitly, to keep the line moving and let quality control handle problems downstream. The result is that defects travel through the system and get caught at final inspection. Or worse, they don't get caught at all, and they end up in the product. Toyota's system is built on the opposite logic. A defect caught at the point of origin costs almost nothing to fix. A defect that travels 3 stations down the line costs significantly more. A defect that reaches the customer costs catastrophically more in warranty claims, in reputation, in lost sales. So Toyota stops the line every time, without question. I've spoken to American technicians who transferred to Toyota plants, and the cultural adjustment is profound. The mindset shift from keep it moving to fix it here now completely takes months to internalize. But the vehicles those plants produce reflect it in ways you can measure with a torque wrench. Simplicity as a strategy. One more thing before we talk about what this means for you. Japanese automakers have, until recently, maintained a philosophical commitment to mechanical simplicity that their European competitors in particular have completely abandoned. Compare the cooling system on a 2010 Toyota Camry to a 2010 BMW 5 Series. The Camry's cooling system has a water pump, a thermostat, a radiator, hoses, and a fan. That's it. The BMW's cooling system has an electric water pump, an electronic thermostat, a variable speed fan clutch, a secondary auxiliary pump, and a network of sensors managing the whole thing. More components means more failure points. More electronic integration means more expensive failures. The BMW cooling system is technically more sophisticated. It's also dramatically less reliable. Toyota engineers ask a fundamental question before adding any component to a vehicle. Does this need to exist? If the vehicle can accomplish its function without it, the component doesn't go in. That approach produces vehicles that are harder to make impressive on a spec sheet, but significantly easier to keep running for 300,000 miles. Honda's philosophy around their naturally aspirated engines reflects the same thinking. While European manufacturers were adding turbochargers to smaller and smaller displacement engines to hit fuel economy targets, Honda continued developing efficient, naturally aspirated engines that didn't require the additional complexity of forced induction systems, intercoolers, turbo seals, and boost controllers. The turbocharged European engines make better numbers in EPA testing. Honda's engines make better numbers at 200,000 miles. What this actually means. Here's the bottom line after 19 years of seeing vehicles from every manufacturer in various states of repair and disrepair. The gap between Japanese and Western automotive engineering is not closing. It's maintained by a set of cultural and philosophical commitments that cannot be replicated by switching to better steel or hiring more quality control inspectors. You cannot buy Kaizen. You cannot mandate it through government regulation. It has to exist at the organizational level, in the way decisions are made and the values those decisions reflect. When you buy a Toyota, Honda, or Mazda, you are not just buying a vehicle. You are buying the accumulated output of a manufacturing philosophy that has been refined continuously for 70 years. The engineers who designed your engine were trained by engineers who built the previous generation, who were trained by engineers who built the generation before that. The institutional knowledge is unbroken. The commitment to the next car being better than the last one is genuine. If longevity is what matters to you, if you want a vehicle that will still be running reliably when most cars have been recycled, the engineering philosophy behind Japanese automakers is not one consideration among many. It is the consideration. That 2003 Honda Accord with 387,000 miles on it, the owner drove it out of my shop that day after a routine oil change. She told me she planned to drive it to 500,000. I believed her.